Welcome to EE12, Quantum Electron Transport. As usual, you're going to find all the material for this course on the iLearn website, shown here. This is the syllabus. These are a number of applications, but we're really going to be looking at sort of the details of how you actually do calculations of transmission coefficients, conductivity, and current fully quantum mechanically. Here are some references. There's no real textbook, although I've typed up the course notes over the last few years, have about 5 chapters typed in, which we will use as essentially our textbook is basically a typed up version of the notes I will be presenting. Other references are shown here. In case you don't like the way I present material, it's always good to see it from different perspectives, different presentation styles, different points of view. So here's a classic book by my advisor, Supriyo Datta, from '95, and then he wrote a second one from 2005. And I think we had these, this was also listed as a reference for the previous course, EE208. And then there's a book by Ferry and Goodnick that also contains good material on non-equilibrium green function theory. So 3 different presentations, and if you want a different perspective on the way I'm presenting the material here. We're going to spend most of the course talking about coherent transport, which means there's no inelastic scattering mechanisms in the device. So it's really, we're just solving Schrodinger's equation to calculate transmission coefficients in numerically efficient ways and recasting Schrodinger's equation in the form of what's called non-equilibrium green functions. But as long as we're only doing coherent transport, except for the way perhaps we deal with the boundary conditions, then even though we recast everything in the form of non-equilibrium green functions, we're really just, it's a fancy way of solving Schrodinger's equation to calculate transmission coefficients. We will, at the end of the course, talk about the second quantization and reformulating the equations using second quantized operators, and hopefully we will go through an example where we include phonon scattering. So, yeah, that's the syllabus. That's the material we're going to be covering. As usual, you will find all the course materials here online on iLearn under course materials. So I'll post the lecture videos of the although I may be putting them on YouTube. I'll at least put links here. We're running out of space for all these videos. Here are the notes I was talking about, the typed up notes. So you will definitely want to download these and have them as a reference. So I've been typing them up for the last few years. Got the first 5 chapters typed in. So the first chapter, which we'll be spending a considerable amount of time on, we start off with Schrodinger's equation, define this basis of scattering states, calculate transmission coefficients, and then recast, simply using algebraic manipulation, recast what starts off as your usual eigenvalue problem into all the expressions that you see in the non-equilibrium green function formalism. So we start off with this typical scattering point of view where you inject a wave from, say, the left side part of it gets reflected, part of it gets transmitted. Your device is just some region in between. And conceptually, it's no different than the scattering problems that you are taught in the physics department. Although they're generally dealing with some spherical scattering potential and using spherical harmonics. They inject the plane wave and then they calculate some scattering cross-section. Here we're also injecting a plane wave, although our geometry is more confined. What comes out the other side is what we're after. That's the transmitted wave. That will give us our transmission coefficient. And conversely, you could inject from the right side and see what comes out the left. We'll discuss both those scenarios. But this is the basic picture that we're going to start with. These scattering states. So a state that evolves from injecting away from the left or from away from the right. All these states combined form a complete basis. It's the basis of scattering states. We'll then move on and reformulate this picture here into a tight binding picture. Just redo it all in tight binding. And then from the tight binding picture, we can bring it down to our usual matrices. And we'll start manipulating the matrices until we finally get things that look exactly like what you have in the non-equilibrium green function expressions. This central device matrix part of the Hamiltonian becomes your green function, or the inverse of the green function. Where do I have it? Right here. So we finally derive this 3x3 device section of the Hamiltonian, shown up here. So this 3x3 device section connected to two infinite leads. We're able to, what the physicists would call, integrate out the leads, reduce the whole thing to just a 3x3 matrix. When you do that, you introduce what are called self-energy terms on these upper and lower diagonal corner blocks, which we will discuss in some detail. And then this is, by definition, this matrix here is the inverse of the green function. And then we just continue to manipulate the expressions, and finally, just by identifying terms, end up with a complete set of non-equilibrium green function expressions that you see in the standard textbook. So the final sort of end of the derivation in Chapter 1 are these set of green function equations that, as I note here, these four equations right here are often the starting point rather than the ending point of the derivation when you pick up, say, an article or book on non-equilibrium green functions. But we spend Chapter 1 getting to this point, starting from Schrodinger's equation and using algebra. So that's what we're going to be spending some time doing during these first several weeks. Let's see, what else do we have? So this is the typed up notes here, so you'll all want to download that. I also sometimes would have students taking the course who had not taken 208, so these are the 208 notes here, but I think you've all taken 208, so that's not an issue. This first part of the point of view that I start off with is Schrodinger's equation and scattering states. The nicest presentation that I'm aware of was given by Bill Frensley in this book chapter, and so I follow that in the beginning relatively closely. So if you want to see the original version, here's the book chapter from Bill Frensley. You can look at that, and he goes through similar steps that I'm going through. Finally working down. I think what I do is I go to this tight binding, single band tight binding model that we became so familiar with in EE208. What Bill does is he starts off with the effective mass equation and then discretizes it using finite differences. But we showed in 208 that this, when you do this, it's exactly formally identical to nearest neighbor type binding. So the form of the Hamiltonian, the discretized Hamiltonian he gets, is exactly what we get from our nearest neighbor type binding model. Tridiagonal, and then he uses the same algebra we use to write, to truncate the device part of the Hamiltonian. And so you can see what he does here. And this becomes the inverse of the green function, exactly the same steps that we're going through. So here's sort of the original version. Again, if you want another perspective in terms of starting off with the effective mass equation and using finite differences to get the same form of the tridiagonal Hamiltonian that we get, just going to a nearest neighbor type binding model. Okay, so that's okay. This chapter by Supero Data. This was also a reference that we had in 208 from his early book from the 80s. It's just sort of the most straightforward discussion I'm aware of starting off with your differential form of Schrodinger's equation and reducing it to the matrix form of Schrodinger's equation using some localized orbital basis set. Exactly what we do all the time, and we did in 208, and we'll continue to do here. Here are some links to some other material. This is more good for some historical perspective that I will also start off the lecture with, and also talks about a non-orthogonal basis. And finally, we get to the more advanced texts that will become relevant when we start talking about second quantization and sort of the formal derivation of non-equilibrium green functions, and put them into the perspective of other green functions like real-time green functions, temperature green functions, etc. A great review article by Mahan, Remmer and Smith, and Yelowitz. And then finally these seminal papers by Caroli et al. And this was the first paper where they used non-equilibrium green function formalism to treat the leads of their device. So they set it up in the same picture of a left lead, a right lead, and a center device, and then treat the leads using self-energies, treat the leads exactly using self-energies in this non-equilibrium green function formalism. So they were the first ones to do it in 1971. And then they quickly had followed up with a series of articles. So they did it initially using tight binding, and they redid it using basically like an continuum effective mass model. And they applied it to tunneling through a barrier and finally electron-photon interaction. So they did all this within 1971 to 1972 or 73, this last paper here. So these are just classic historical papers of the very first time negative was used for essentially device modeling. And if you look at the citation rate of this paper, it gives you some idea of how popular this method was for modeling quantum electron transport. So this was published in 71, and so during the 70s this paper was cited about 20 times. During the 80s, maybe 25 times. During the 90s, a couple hundred times. During the 2000s, maybe 300-400 times. This is highly unusual for a paper. Usually the citation rate, peaks out relatively soon after a paper is published and then starts dying off. Whereas, this paper was for 2 decades, wasn't cited, was maybe cited 50 times in 2 decades, and then suddenly it just explodes. So during the 90s and 2000s, it's cited hundreds and hundreds of times. Highly unusual. But it also is a good indicator of how popular the non-equilibrium green function approach became for performing full quantum transport calculations for device modeling. This is a good indication of the popularity of the method. The same thing is true for this book by Supriyo Datta that we were just looking at from 1995. Initially, it wasn't cited much at all. So it was published in 95, this one here. And then sometime, maybe early to mid 2000s, the citation rate suddenly took off. And during the 2000s, it was probably cited 1,000 times and continues to be very highly cited. Probably been cited over 2,000 times now. So again, it's sort of interesting that this book that was written for graduate students, and I think it is a good text for graduate students, took about 10 years for it to really catch on. And it's sort of interesting that a book written for graduate students was also about 10 years ahead of its time. Even something about this non-equilibrium green function formalism that took a while to catch on. Maybe because, it's sort of, if you can do it with Schrodinger's equation, which everyone probably feels more comfortable with initially, the feeling is why introduce all this, heavy machinery of non-equilibrium green functions is the way many people might view it initially. But it turns out to be gives you a lot more flexibility, as we'll learn as we get in deeper into this course. Okay, so that summarizes the material available that we have uploaded here on iLearn. And now I'd like to give a little overview of a little bit of history on how we got to where we are today in terms of what we're interested in, and really the experimental impetus or motivations to do this full quantum mechanical device modeling that's become so prevalent today. So, back in the early 80s, the electrical engineers really weren't doing much in the way of quantum device modeling. Their quantum device, the sort of well-known effects were Zener tunneling, where you tunnel from the valence band to the conduction band, and energy quantization, sort of particle in a box quantization, so that in your CMOS transistor, the confinement potential, so here you would have the SiO2, then you have your silicon, and in here at the interface, when you've inverted this, you get some energy quantization of the states here. So people were aware of this, and the greatest review, one of the greatest reviews of all time, certainly the greatest review for silicon, is a review by Ando, Fowler, and Stern in the Review of Modern Physics. I think it was published around 82. And so they spend some time analyzing these type of quantum mechanical effects, such as the effect of the quantization of the electrons in this triangular confinement potential. But they really weren't doing what you would call full quantum device modeling, using some quantum transport formalism to calculate current voltage characteristics. The prevalent, approach of the time, the sort of hot research topic of the time was in the early 80s, hot electron effects. And if you think about where we were in the 80s, we had a VDD of about 5 volts. And this oxide barrier is about 5 volts. So the voltage was high enough that as you went from source to drain, it was possible to kick highly energetic electrons into the SiO2. And when that happened, you would get charging effects, unwanted charging effects in the SiO2, which would shift your threshold voltage, and that's not a good thing. And to model these highly non-equilibrium effects, these high energy effects that are happening way away from the conduction band edge, 5 eV, way up in the conduction bands. What people were doing then was full band Monte Carlo, a full band Monte Carlo solution of the Boltzmann transport equation. So this was sort of the state of the art, and where most of the focus was in the early to mid 80s. And then sometime in the late 80s, two things happened. And we entered what I call, I don't know what other people call it, what I call the mesoscopic era. Mesoscopic. And this is sort of late 80s. To around 93 or so, maybe at the latest. So 88 to 93, about a 5-year period. And two experimental sort of capabilities provided the impetus for this. One was the extremely high mobility two-dimensional electron gases in gallium arsenide AlGas systems. So high mobility, what people refer to as 2DEGs, two-dimensional electron gas. And the system people were growing back then was the gallium arsenide L-gas system. So in this system, this is what you grow a high electron mobility transistor with. You have your wide bandgap L-gas material, your narrow bandgap gallium arsenide. So this interface looks kind of like what we drew for the MOSFET. So this is going to be your gallium arsenide. What I'm drawing here is a conduction band edge. This is your L-gas. And in this system, you place the dopants back here. You do what's called delta doping. So the dopants are away from, the electrons are sitting down in here. The dopants are moved back some few microns. The energy level of the dopants is up here, so they will eventually tunnel out. Once they tunnel out, they fall down into this state here, and then they're unable to get back. So you have the electrons separated from the dopants by several microns. And because of that, you reduce the ionized impurity scattering, and so you can get extremely high mobilities. And they were getting mobilities on, at liquid helium temperatures. They're getting these at Bell Labs of like 10 to the 7th centimeters squared per volt second at liquid helium temperatures. And so because of the mobilities are so high, you could, the electrons would go on the order of a micron or two, phase coherently, quantum mechanically phase coherent, and act like waves. So, one of the devices that everyone found so interesting at the time was this Eronel Bohm ring, where you would send in your electron wave, and you have to think of it like a wave to understand it from one side. There's two paths that it could follow, like this, come back together, and then come out here. Now, if you can change the phase control the phase of one arm with respect to the other, then you can modulate the conductivity of this ring. Okay, so there's conductivity. And the way you control the phase is by applying a perpendicular magnetic field. And so the phase depends on the magnetic flux quantum contained in the ring. And as this changes by integer multiples of the magnetic flux quantum, your conductivity goes up and down, because it's as you change this phase by pi of one arm with respect to the other, you get constructive and destructive interference. And so people would actually see this and measure this. And to model this, you need a fully quantum mechanical model, because this is a fully quantum mechanical effect. At the time, people were also modeling the quantum Hall effect. So experimentally, this is the first thing an experimentalist will do when they have a high mobility electron gas. They'll build a Hall bar. You have your magnetic field everywhere, say perpendicular. You send in your current, and you're going to measure your Hall voltage, and at high enough magnetic fields, you get the quantum Hall effect. And you can model this using Negev and actually see the quantized sigma xy, and you can see the edge states that develop here in the spectral function, and all of this pops out nicely from your fully quantum mechanical model. So this was the mesoscopic era driven by these. Well, this was one. So this was one driver, the ability to make these very high mobility electron gases. The other driver, I would say, was E-beam direct write lithography. It was just really getting going at the same time, allowing people to define these relatively small structures. So these were the two experimental drivers. One, you had these very high mobility two-dimensional electron gases in these gas-outgas systems, and then using E-beam direct write, you could make these structures on the. So the length scale we're talking about in the mesoscopic era is on the order of a micron. So from half a micron to a few microns, that's the length scale we're talking about, because these high mobility 2DEGs allowed you to have phase coherence over that kind of length. Seems rather long now, but so this was a mesoscopic era. So if you haven't heard that word before, meso simply is what's in between micro for microscopic and macro for macroscopic. Mesoscopic. And then following that, we moved into what I would call the single electronics. In which structures could be made so small that if you had one electron sitting here and tried to put another electron in, the charging energy due to this electron was so large that it would block this electron from coming in. It was called Coulomb blockade. And this, Professor Korotkov was very active working in this area. Negative probably wasn't used so much for this as extensively. It was attacked more using rate equations. There was some aspect to it that was very classical. And this quickly gave way. So single electronics started coming around in the early 90s. But it quickly gave way in around 95-ish to molecular electronics. So molecular electronics kicked off sometime early to middle 90s. I'll just throw out a round number of 1995. And it went to around, throw out another round number, 2005. So around this time in the early to mid 90s, DARPA made a large investment, the Moltronics program, which really got everyone's thinking about this. And so in the molecular electronics, people were interested in modeling transport through molecules. So this is supposed to represent a benzene ring with some linkers, and you have to connect it up to some, macroscopic. So this is supposed to be like an STM gold or some kind of metallic STM tip. So you're hooking up a molecule. These are supposed to be the atoms of your metallic leads, hooking up to some molecule, and the classic molecule that everyone initially looked at was a benzene ring. And so in the molecular electronics era, this is when Negev really became sort of the standard method for doing quantum transport calculations. So the father of molecular electronics, Mark Ratner, collaborated with Supriyo, and they wrote a paper on using Negev to model transport through these systems. And so Ratner's group used it. They just used Negev to do all of their modeling. Han Guo up at McGill at the same time published a paper using non-equilibrium green functions to model electron transport for these type of systems. And their code eventually became what's known as the atomistics code. It served as a starting point for what is now atomistics. And everyone else pretty much followed suit. So during the molecular electronics era, what people had to do really pretty much seriously for the first time, they were combining your density functional theory codes such as Gaussian, it's a quantum chemistry code, or siesta, anything that was a localized orbital density functional theory code. So they were combining that with the Negev with the non-equilibrium green function formalism. So there were these existing density functional theory codes that people had used to model molecules for a long time. But of course, no one had thought about doing transport through a molecule like this from sort of this device point of view. And so these codes needed to be the existing codes, like the quantum chemistry code of Gaussian or the DFT code Siesta. They had to be somehow modified and incorporated into a Negev code. And so that's what everyone did during the molecular electronics era. Really, probably I would say for the first time. No one had really thought about doing that before. But, you know, when you were faced with modeling a molecule, it seemed just the obvious way to go, to take the existing codes, which were very good at modeling molecules, and then extend them to do transport. And the way they were extended was using non-equilibrium green function formalism. So it was really during this molecular electronics era that Negev became sort of the standard approach for doing quantum device simulation. And it was also during this era when Supriyo book, written in 1995, you know, the citation rate to that just really took off. And also the era when the citation rate to Caroli's first paper from '71 really took off. Okay, so there's molecular electronics. Well, what killed molecular electronics? Well, all these things just die a natural death after a while. But unless they show some great breakthrough. But really what came next was graphene and 2D materials. So this is, we're still in this era, going from, I don't know, we'll just round it off, say 2005 to the present. And this is where we are now. And there are so many materials being considered, sort of such a deluge of new materials, that I would say there's really two options. One is you've got to be very good at determining empirical tight binding parameters for each new material that comes along, or you use the existing density functional theory codes and combine them with a non-equilibrium transport formalism. So this is where we are now, and after the last decade, this non-equilibrium green function formalism is sort of the standard method for doing quantum device modeling. So with that, it's time to, that brings us up to where we are now. And now it's time to start discussing the theory. So, in 208, we really focused on calculating the what we call the EK relationship of crystals, the energy versus momentum relationship. And to do that, you define your primitive cell. You have periodic boundary conditions. You send it off to your eigenvalue solution solver. You generate this E versus K plot. And from that, you get a lot of useful information like velocity, effective mass, density of states. We even talked about the imaginary wave vectors determining your tunneling. But now we have to move beyond that if we want to do transport. One of the key differences to what we were doing then and what we're doing now is now we're really talking about an open system. Where you have a device region, which is a region of interest, and it's going to be connected to a left lead and a right lead, or a left contact and a right contact, and these are really reservoirs. You can think of them as thermodynamic reservoirs, which can inject and extract particles, electrons and holes, from the system of interest, namely the device. So the abstract picture to set up the problem is this, where you have a device region and then you have your left lead and your right lead. So we'll call this point X sub L, X sub R. So over here is our left lead. Over here would be our right lead. And say, to begin with, the way the problem is set up, it's set up as a scattering problem. So you've all taken a quantum mechanics course out of the physics department. So in physics, you talk about scattering problems. Usually you have some spherical potential. You send in a plane wave, and you get out a scattered wave. And you talk about a scattering cross-section, sigma. And there's various ways you analyze it, usually all within using spherical harmonics. So that's the scattering picture that you use in physics. So the math is different because you're doing this usually in 3 dimensions using spherical harmonics and worrying about the scattering angle and stuff like that. Here for the device, the geometry is a little simpler. Everything in the beginning of this course, it will be strictly one-dimensional. So here we also send in a plane wave. It's just a one-dimensional plane wave. So then this will be e to the I KL x minus x sub L. So that's my forward-moving plane wave that I'm sending into the device. And so out in the leads are considered ideal regions where there's, let's say it's all the same crystal. So this is a region of the crystal where there's no macroscopic electric field. It's just your ideal crystal, the periodic potential of your ideal crystal in the leads. So this plane wave is coming in as just an eigenstate of one of the block states of your ideal crystal in the lead. In the device, this is where the potential is varying, so we're going to have some variation of the potential in the device, and so therefore there's going to be some reflection of this plane wave. So some of it's just going to be reflected back into the lead. And this reflected wave is just R sub has a reflection amplitude R sub L e to the minus I because it's moving in the opposite direction KL. I need more room. X minus X sub L. Okay, so that's my reflected wave. So I send in this plane wave. Some of it's going to be reflected, and some of it's going to come out the other side. It's my transmitted wave with some transmission amplitude TR e to the I KR X minus X sub R. Okay, that's my transmitted wave. And so this K on K sub left, I'm sending in my device region. I mean, if we think in terms of a conduction band profile, let me copy and paste this to the next page. Okay, so if we think in terms of a conduction band profile, over here in the lead, there's no electric field, there's no potential variation, by definition of what we call a lead. In the device, and the same on the right hand side, and I can have a potential, so the conduction band could be at a different potential on the right than on the left. And in the middle, there's some kind of potential variation going on in the quote device region. Okay, so this is a pixel in terms of, say, a conduction band edge. And everything we're doing now, for all of Chapter 1, for a while, will be what's called coherent transport. I want to emphasize that. And coherent transport means it's elastic. So if you send in an electron at one energy, it stays at that energy. And it comes out the other side at that energy. Okay? It's elastic transport, coherent transport. And so, if you think of a simple parabolic model, this kinetic energy here, the distance from the band edge, is going to determine the wave vector on the left side, and this energy here will determine the wave vector on the right side. The energy is the same. The wave vector changes simply because you have more kinetic energy when you come out the right side. Okay, so this is the picture in terms of a band diagram, what we're talking about. And similarly, I can set up the same thing where I inject from, inject from the right side. So I can inject from here, and this would be e to the minus I kr x minus x sub r. Some of it would be reflected, r sub r e to the I kr x minus xr, and some of it would come out on the left side, the transmitted, with the transmitted amplitude. I'm sorry, T left. K left. Okay. So you can inject from the left or the right, and a good deal of this course will be calculating these transmission amplitudes, which then give you the transmission coefficients. All right. So formally, if you look at these scattering states, let's just say a few words about scattering states. So what we've drawn here are what's called scattering states. So if we consider the situation where we're injecting from the left. So if we inject from the left with this e to the I, k left, x minus x left, the state that evolves from this injection of this plane wave, this is the scattering state. So it includes this plus the reflected component plus the transmitted component plus whatever wave function you have in the device. I'll just call it psi device. Plus whatever, so this is the full scattering state. And we sort of label the scattering state as just, so this represents a full state that evolves from injecting a plane wave from the left, and part of it's going to come out the other side, part of it's reflected. You'll create something in the device. All of that is this scattering state. Similarly, you can inject from the right-hand side, going the other way, as we did down at the bottom of the page here. And so we would define that state as simply the state that involves from injecting a wave vector from the right-hand side. And this total set of states, KL, KR, for all possible Ks, left and right, they form a complete basis, complete orthonormal basis. Well, maybe not normal. We haven't normalized them because all we need is ratios. So as you can see, these aren't normalized, and we'd have to divide by some square root of length to properly normalize them. But they are orthogonal. If it's not the same k, they integrate to 0. The only exception to this is when you have a situation where, say, this is my conduction band in the left. It's supposed to be flat, sorry. Here's my conduction band in the right. And in the device, if I have a situation like this, with some state down here, that's a bound state below the continuum on both the left and the right. The scattering states can only account for all of the states above this energy here. And so to put in bound states, you would have to actually add that to your basis set, whatever bound states that might occur in the device. But usually in practice, we don't need to worry about that. And we can discuss that much later in the course as to why we don't need to worry about that. So for now, for everything we're going to derive, you can think of these scattering states as a complete basis with which we can describe. So by summing up scattering states, we can describe the wave function in the device, which is what we're really interested in. Okay. Let's talk about flux and current continuity. Okay. So let's think. First of all, let's remind ourselves of what is flux. So flux is some density. Let me call it N for electron density, because I'm not interested in the charge at this point. Density times velocity. That gives me flux. And so for us, quantum mechanically, we'll replace that density by the magnitude squared of a wave function. times the velocity of that wave function. And this wave function will be whatever associated with some incident. Let's say we're injecting from the left with some incident k sub L, right? That would be our flux associated with some incident plane wave KL on the left, okay? This is what we mean by flux. And it's similar to, you know, the very first, it's just really current where you divide out the charge, right? I mean, the first expression you learned for current in freshman physics is that J equals rho V, right? Well, in this case, rho is your charge density, which is just your electron density times Q. So we're just defining the flux without the charge. Okay. So the incident flux, I send in my plane wave. E to the I KL x minus XL. So the flux associated with this is, well, the velocity associated with whatever k I'm at, k sub L, right? Times psi squared and that's just 1, right? So that's just V sub L, not worrying about the units, because we're going to take a ratio at the end of the day. Okay, so that's the incident flux. So this is incident. Due to that incident plane wave. And now we have the reflected part of this flux that, you know, is being injected to my device. Part of it's reflected. And so that reflected flux is, well, it's negative. Same energy, same K, so it's just we reverse the direction of the velocity, right? And the magnitude squared of this wave function is just RL squared, right? So this is the reflected flux. And then finally you have the stuff coming out the other side. Your transmitted flux with a transmitted amplitude T sub L. And this gives you take the magnitude squared multiplied by the velocity. That gives you, I'm sorry, TR coming out the right-hand side. TR e to the I KR. So that just gives you V on the right-hand side, magnitude squared of the wave function. So this is your transmitted flux. And now flux has got to be conserved, so that means that the incident flux, VL, minus the reflected flux, VL RL squared, has got to equal the transmitted flux. Right, so the incident flux, the total has got to, another way to think about it is you send in so much flux, and you got to account for it. So part of it's going to be reflected, part of it's going to be transmitted. The sum of the reflected and transmitted has got to be what you send in to begin with, because nothing's lost or gained. So in other words, VL is equal to, another way of saying that is that I can move this onto the right-hand side. So there's two components of the incident flux. Part of it's reflected, part of it is transmitted. And so if I combine this, I have the VL times 1 minus RL squared is VR times TR squared. And the same thing holds for if I inject from the right and come out at the left. I'm going to have VR times 1 minus R sub R squared. It's got to equal what comes out on the left side, VL times TL squared. So this is when I inject from the left. And this is when I inject from the right. Okay. And all that is simply a statement of current conservation, flux conservation. What you send in has got to be accounted for. Either part of it's going to be reflected, part of it's going to be transmitted. The whole thing has to add up to what you started with to begin with. Let's talk about one of the most important things you're going to be calculating. We'll spend a lot of time figuring out how to calculate efficiently, and that is the transmission coefficient. Put this in red. Okay. Or it's also called the transmission probability. Okay, so what is it? The formal definition is the ratio of the transmitted flux to the incident flux. Okay, that's the definition, the fundamental definition of what we mean by the transmission coefficient. Okay, well, we're looking at the fluxes, so let's take a peek back. So look at this up here. The incident flux is just V sub L. The transmitted flux is just VR TR magnitude squared. So we just have to take the ratio. So T is equal to, the transmitted flux was V right, T right magnitude squared. The incident flux was just V left. And so we have that the transmission coefficient is the amplitude of the transmitted wave magnitude squared times the ratio of the velocities, the ratio of the final velocity over the incident velocity. This is a fundamental definition. It's completely general, generic. We're going to be coming back to this a number of times and showing that what we derive with our non-equilibrium green function approach is simply this. This is your transmission coefficient. And then the reflection probability is defined similarly. So reflection which is usually just denoted as uppercase R. It's again defined as a ratio of the reflected flux over the incident flux. Well, the reflected flux is just the magnitude squared of your reflected wave function. And say we're doing from the left-hand side, so that's R sub L magnitude squared times the velocity. And the incident flux is just the same velocity, right? Because all this does is it keeps the same velocity, just reverses directions. So this, your reflection probability, is just the magnitude of the reflected wave function squared. The amplitude, what do I want to say? Amplitude, magnitude squared, amplitude, yeah, anyway, R sub L magnitude squared. And if we look back at, we were talking about current conservation here, take these expressions, which were our expressions for current conservation. So if we divide through by V sub L here on both sides, we just get that and move the RL squared to the right hand side, we get that 1 is equal to R sub L squared plus TR squared times VR over VL. Right, just from this expression over here in red, which means that 1 is equal to R, big R plus T. And this is why they're probabilities. Again, this is just a statement of current conservation. So T plus R equals 1. It's just a statement of flux conservation. You send in a flux of 1, some of it's going to be transmitted with some probability, some of it will be reflected with some probability. The sum of the probabilities had better equal 1, right? So T, your transmission probability plus your reflection probability, is equal to 1. Okay then, that's sort of the basic picture of behind device modeling with Schrodinger's equation.